let's solve the yxx minus 1 over c0 squared ytt equal to delta x minus c times delta t minus tau. So let's solve this problem. Okay. And with yx0 equal to 0, y velocity x0 equal to 0. This is good because for the if you do right, so that maybe we'll use that later. Yeah. So this is our spatial loading. Okay. If I call this equation stop, so we do Fourier transform on equation stop. Okay. Then we have a note. The Fourier transform of fn's derivative function with x is equal to minus I omega or n power to the f hat omega. Okay? So this omega is our new variable. If I use gamma, okay, for this case, our gamma. All right? Note this, because here we are going to focus on equation about x, right? We change the x variable. Yeah. And we also know the integration square root of 2 pi minus to infinity the delta x minus c with the ei gamma x dx. It's just put the value on it is 1 over 2 pi, and this is the ei gamma c. Okay, just put the only non-zero at x equal to c. That's why we have this point. Okay, so this is a very standard. You can prove it. Yeah. All right. So let's do it. Okay. So after we did the Fourier transform about equation start, we have the minus gamma I gamma, okay, minus I gamma square y bar, okay, we use y bar, okay, and minus 1 over c0 square and y bar double dot, okay, y bar tt, tt, partial derivative of t, okay, and this equal to 1 over square root of 2 pi, because if we do the Fourier transform, use this equation, right, about this part, and this will be ei gamma c, and keep the delta t minus tau here, okay, because we have the Fourier transform nothing to do with this t domain function. All right, and this is I square gamma square y bar actually is equal to minus 1, so this is minus gamma square y bar minus 1 over C0 square y bar tt equal to 2 pi e I gamma per c delta t minus tau. All right? All right. So after this, we got the equation, for example, called this double cross. Okay. Then we apply for Laplace transform. Laplace. On equation double cross in t, in time domain. Okay? So first we transform to x domain to gamma. Then we transform the time domain to another domain, t, we call the p. Okay? Laplace transform is in this 0 to infinitive ft e exponential minus pt dt. Okay? So you learned before you use s minus st. So here I use p as a variable. Okay? When you learn Laplace transform, you will use s to represent a new variable, right? And this is a original function. We transform the time variable on it. All right, and ft. The inverse of Laplace transform is do what? We do the 1 over 2 pi I, and the integral line minus I omega to c plus I omega, I infinity, and f bar p e pt dp. Okay, so this is inverse. It's a inverse Laplace transform of f p. Okay, so this is a Laplace transform of f t. Okay, this impression. So this is what you learned before. But you didn't learn how to do the inverse by integration. You just use some formula, right? But actually, this is the real equation for when you do the, you got a solution of this, you want to transform back to time domain, you have to do this. And this is a complex plane integration. So this is a P plane. This is a real part, this is imaginary part. So in doing the integration, the contour is this contour from, this is distance c. So this is a c plus minus infinity, I infinity. To this point is c plus I infinity. So this, for this point, is a c minus I infinity. This is c plus I infinity. Okay? And when you do this integration, you have to choose a suitable c. Suitable c. Let all the pole point, the singular point, let all the singular pole point. This is a pole, pole, okay, of f hat p. So that means this at this point, p has singularity, okay? So there's singular point. So you have to choose an integration line that all the singularity just in your left-hand side, okay? So this is we call the Bromwich. Bromwich contour. Okay, So that when you learn the complex variable theory, probably you will learn the Laplace transform inverse, how to do the integration in complex plane. 你们学了吗？你有讲？你讲，OK， 好。Anyway， 这是书上有了，我们也大概一般人都是 ，usually we just use a formula to get inverse from Laplace transform. Okay. So I say the C value, okay, the C value determine your the path of integration, okay. So make sure the path of integration, all the poles are on the left side of your path of integration, okay. All right. So when we do Laplace transform about this, we can have minus gamma square y bar hat, okay, y bar hat minus 1 over c0 square p square y bar hat, okay. So this will become a variable gamma and p equal to 1 over square root 2 pi, okay, and E I gamma c, and similar for this integration to deal with this, we have exponential minus p tau, okay, at tau, put p t equal to minus tau, p tau, okay, p tau. So this is my equation after two types of transformation. So this is algebra equation. Okay. Actually, this is a second order differential equation. You can solve in time domain also. Okay, but here we try to use two transform. So this is algebra equation. From here, I can get y bar hat. Okay, so if I call this equation delta, okay, so from equation delta, we have y bar hat gamma p is equal to minus c0 square over square root 2 pi 1 over p square plus c0 square gamma square exponential I gamma c minus p tau. All right. So we got this. Then we have to back to gamma, the t domain, and back to the x domain. All right, all right. So let's further do the Laplace inverse first. Okay. So let's recall. In Laplace transform, Laplace inverse, p square plus c0 square gamma square is equal to 1 over c0 gamma, okay, square. Oh, c0 gamma sine C0 gamma t. Okay. Okay. And Laplace inverse of the form exponential minus p tau f hat p. This will be equal to f t minus tau. We call this t shift. Yeah, t shift. Okay. If you find something familiar with function of transform function, then it times with the exponential minus p tau. So just do a tau shift. Okay. So this is for t minus larger than tau equal to 0 for t smaller than tau larger than 0. So this expression can be written into one form is f t minus tau heavy side t minus tau. So when t is smaller than tau, this term equal to 0, right? When it's larger than tau, equal to 1. So that will be this ft. Right. So the h is a heaviside function. Okay. Okay. So now let's have look at. Okay. We have this is constant, right? So take out. And we have this and exponential p tau. Okay. Right. So we can see. All right. Exponential minus p tau with exponential I gamma c, right? So we use these two formula. We have a 1 at y bar. Now we from gamma to time t s. Okay, and this constant c0 square 2 pi, keep it, and e I gamma c, keep it. And this term will be use a sign. This will be sine C0 gamma. But t, now we have a shift. T minus tau. And with 1 over C0 gamma, right, for this term, inverse. And with a heavy side, T minus tau, right? Okay. All right. Okay. So this is why these things, right? So our xt will be y bar. We'll do the integration 1 over square root 2 pi minus infinity to infinity y bar gamma t exponential I gamma x d gamma. Right? Minus, right? Minus, is that right? Right. Minus Right, minus. Careful, it's minus here. Right? So we put everything into it. So then we get yt is equal to minus heavy side t minus tau. And we have this will be 2 pi. And it's t, sorry, gamma, gamma, sorry, it's gamma x, right? Right, gamma change to x, so it's okay, C0 square, keep it, and yeah. Okay. So this the integration minus to infinitive sine sine C0 gamma t minus tau, okay, divided by C0 gamma exponential minus I gamma x with I gamma c is minus I gamma x minus c d gamma. All right. So this is what we get, this solution. I think this is already to the extreme of our mathematics in civil engineering department, okay? Even maybe in applied mechanics. So this is what we have. Okay, so this is solution of this, yeah. Okay, see what we can do further. We can do further, right? So now we want to use the Fourier inverse of the function square root of 2 over pi sine A gamma over gamma equal to 1 for x value larger than A. That's smaller than A, sorry. And equal to 0 for x larger than A. Okay, it's very